All right. In this section, we're going to cover second order linear differential equations and just understanding what they are and then how to solve them. Unlike first order, second order techniques are really just one technique we're really going to focus on in this class, which is going to come down to solving quadratic equations most of the time. So in a way, it's a lot easier than first order because the techniques kind of feel more grounded. The only thing is with second order, it's more about recognizing different cases and applying the correct the correct solution type to a specific type of differential equation. So first, let's discuss what a second order differential equation is. So a second order, which just means two derivatives, differential equation, is of the form. So there's many different ways people write this, but one way could be something like p of x y double prime plus q of x y prime plus r of x y equals g of x, right? This is just a any second order differential equation where p of x, q of x, r of x, they're just coefficients and they can be any function except they cannot contain y. Okay. So where p of x, q of x, and r of x do not contain y. Otherwise, it would not be linear, and that's kind of the thing that we want to focus on. Uh, this makes the equation linear. So I'm going to say second order linear differential equation a lot because that's going to be the focus of this section. Nonlinear differential equations, especially second order, very difficult to deal with. We kind of don't deal with it in this class. There's just not really any good techniques that we know, or even really just in general, that solve them very nicely. You kind of have to use a lot of tricks or manipulations, or just numerical methods. That's usually what we do. So we're going to focus mainly on linear, okay? Now, in the beginning of this chapter, we're not going to look at the what we call the non-homogeneous case, basically that g of x. We don't want it to be equal to anything. We want it to be zero, in fact. So, a homogeneous differential equation, sorry, let me say it this way. A homogeneous second order differential equation will be where g of x is equal to zero. Okay. That's all homogeneous means. It just means equal to zero. Okay. Thus, we have p of x y double prime plus q of x y prime plus r of x y equal to zero. But even more than that, we say, okay, we don't even want to deal with this this coefficient that has x in it. We want to make it even easier. So we're going to say, okay, let's make q of x, r of x, and p of x, let's make them constant, right? So that's going to be the next kind of reduction or assumption we're going to make is, okay, so we also assume that p of x, q of x, and r of x are constants, meaning that we get a y double prime plus b y prime plus c y equals zero, where a, b, c, whenever you see this, it just means they're real numbers. They can be any number you can think of, except, of course, imaginaries like I and stuff like that. So this is going to be the equation that's going to govern the next four sections. 3.5, we make g of x not equal to zero, and then we analyze that scenario. So like this is the equation that kind of governs this entire chapter. And you just have to be very comfortable with this type of equation. Um, and so we think about, okay, what is a solution to a differential equation, right? So remember, a solution to a differential equation is a function that makes both sides equal. That's it. That's a solution to a differential equation. And so if you remember, for us, in algebra, it was always a number, right? In differential equations, we're just saying it's no longer just a number, it can also be a function. So we think to ourselves, okay, can I think of any function that I can plug into a differential equation with two derivatives, right? That means this function has to be differentiable two times, and it's going to cancel itself out completely and get me whatever is on the right side, which in this case is zero, right? Well, if you think very, very, difficult about this, or you think very critically about this, you think, what function can I take the derivative of and, maybe get the same thing or get something very easy? And you think, hey, zero, right? So what if I say, okay, let y, because your dependent variable is the solution, y equals, right? Let y be equal to zero. Then y prime is equal to zero. And y double prime is equal to zero. The derivative of zero is zero, right? There's no argument against that most of the time. So then we just plug into the differential equation. So a times zero plus b times zero plus c times zero, well, that's equal to zero. We know anything times zero is zero, so we just get zero equals zero. So we have something that works. So this tells us two things. Number one, a constant solution is still fine, right? We can still get solutions that are just numbers. But this also tells us that no matter what second order, linear, homogeneous differential equation you have with constant coefficients, um, in this case right now, the answer y equals zero is always a solution. So we can say that in words. So for all homogeneous second order linear differential equations, y equals zero is a solution. It turns out that for any homogeneous differential equation, linear or nonlinear, okay, as long as zero is in the domain, the answer is fine, right? But we're not there yet. We're just saying for this type very specifically, right? This also, because every single scenario has this, we call this the trivial solution. So this is also called the trivial solution. So y equals zero is always a solution. That's nice. And you'll often see this in the homework or just in general mathematics, where if they ask you a question about these types of differential equations, they will specifically say in a direction, give me a non-zero answer, because y equals zero is always an answer, right? So they just want you to avoid doing that. Now, that's great, but in the long run, that doesn't tell us anything. It's just, well, y equals zero. That's like usually it's called trivial too because it doesn't really give you anything, insightful most of the time. So we think of a different equation, right? So we say, okay, what is our goal? Our goal is to find a solution to a y double prime plus b y prime plus c y equals zero. Like that's what we're trying to do. Okay. Which will be y equals some function. Okay. What could that function be? Well, again, you're taking two derivatives, and you don't want to take derivatives of a function that changes it, right? Like here's an example. If you take the derivative of sine, well, you get cosine. It's kind of hard to combine sine and cosine together because they're not the same function. So you think to yourself, okay, I need a function that when I take its derivative, it doesn't really change that much. And zero was perfect, right? It's zero. But I think to myself, there's this weird function that we know that whenever I take the derivative, nothing really happens to it, and that is the exponential. So you think, okay, and you're wondering, how would I ever have thought to think about this? You probably wouldn't have, honestly, but some very, genius mathematician, he just said, hey, that function works. Why not try it? right? That's kind of the idea. It's just we're just guessing and checking, and maybe we'll hit something. Of course, you can derive these more elegantly, and you actually maybe pop out an exponential. But in this case, it's just we're guessing, and we're just hoping it works. If it doesn't, we'll try something else, right? So we say, okay, we're gonna start a new page for this. So we say let y be equal to e to the rx. That's our function. So taking derivatives, we get y is just equal to e to the rx. If we take the derivative, we get, so the derivative of e to the x is e to the x, but the derivative of e to the rx, right? So you have to know r is a constant. So it's going to be r e to the rx. Now, if you're wondering why is it r e to the rx, it's called a chain rule. You take the derivative of the outside, y e to the rx. The derivative of the exponent, which is rx, becomes just r times 1, right? This is a chain rule property. So e to the rx times r times 1 is essentially what happens, right? It's a chain rule. So then you take the derivative of again, and then you take the derivative of r e to the rx, so you get r times r, which is r squared e to the rx. Again, chain rule. So let's write that down just so you know. Chain rule. Okay? Now, one of the things that we learned in chapter one is if you want to verify something as a solution, you just plug it in and see that the left side equals the right side, right? So we're going to do that. So we're going to say, okay, sub in the derivatives above into ay double prime plus by prime plus cy equals 0. And what we end up getting is the following. Again, if you try doing sine and cosine, what you would realize is that you would have sines and cosines, and they're not really easy to get rid of, right? You'd have to do very intense trigonometric manipulations. But here we don't have to do that. Okay? And we notice, right? Hey, e to the rx, e to the rx, e to the rx. They all share the same thing. And we know in mathematics, when everything shares something, we can just factor it out. And that's what we do. Factor it out. So one of the things that you learn in algebra, you might have even heard the name, but people don't remember it ever. It's called the zero product rule. Okay, this is all it says. When you have two numbers multiplied together and they are equal to 0, then we have to guarantee one of them is 0 because that's the only number that does that. 0 times anything is 0. And so if two things that you don't know what they are being multiplied equals 0, then one of them has to be 0. Well, here's the interesting part, right? E to the Rx can never be equal to 0 because an exponential function is asymptotic to 0. It actually approaches it, but never reaches it, which means the only option that we have to be 0 is the right side, the AR squared plus BR plus C, right? Actually, I'm going to write it this way. So that, and then we'll say since e to the Rx cannot be equal to 0, then only AR squared plus BR plus C equals 0. And that is the magical equation that's going to solve every single one of your problems. So if you're wondering, okay, I'm not going to watch this entire video, you just tell me what I need to know. It's right there. That's the box. That's it. It's called the auxiliary equation. That is how you're going to solve every single problem in 3.1, 2, 3, 4, 5. 3.7 and 3.8. They're all going to use this. They have to. It's part of the process, right? So, do I have to do this derivation every single time? No. And that's the thing I want you to understand in differential equations. Once you've done the derivation once, you get to skip it. You get to go right into the end result. And that's what we like about differential equations. Skipping all of that. Okay. So here's the good thing. We look at this equation and we realize that's just a quadratic equation. Why do we like quadratic equations? Well, most people don't like them, but as a mathematician, why do we like quadratic equations? They have a nice solution. It's called the quadratic equation. Sorry, quadratic formula. So that's what we're going to use to solve this, right? So the equation AR squared plus BR plus C equals 0 can be solved using the quadratic formula. Okay. Now, usually you're used to it with the letter x, right? Ax squared plus bx plus c. So do not let the r throw you off. It's just the letter x in the formula's mind, right? So instead of x equals, it's going to be r equals. So r is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And guess what? That's the solution to every single differential equation in 3.1 to 3.4. There it is, right there. So if you're wondering, how many formulas do I need to memorize for this chapter? Well, really, this is the big one you have to memorize is the quadratic formula. If you can factor or complete the square, I mean, sure, those will work too. But at the end of the day, you can always use this, right? And 3.1 is going to look at one case. 3.2 is kind of a setup for the rest of it. 3.3 looks at one case, and 3.4 looks at another case because it turns out that there are three cases that you have to analyze with this equation or this formula. So three of the four next sections are just analyzing each case individually. So it feels like there's a lot of material, but you could really just condense down 3.1, 3.3, and 3.4 into one section and just call it the solution to the auxiliary equation. So it's not as much as you think it is. It's just spread out a lot, right? So there are three cases that depend on so the radical is the most important part of this formula because depending on the value inside, it changes what type of solution we have. And that radical has a name in case you ever are searching online. This is called the discriminant. Not sure why it's called that. Sure, it's related to a German, French, Latin word. Usually that's where most math words come from. So depending on whether it's positive, negative, or zero, you'll have a different type of solution. So the first case is when the inside is greater than zero. It's a positive number. Then this is what we call the real distinct root case. So you have two real distinct roots. I say R1 does not equal R2. And this is going to be 3.1. Like that's 3.1. The second case is when you have a negative number. So you're going to have two complex roots. So that's going to be R1, comma 2 is going to be equal to some alpha plus beta I value. So some complex number we're going to say, right? And that'll make more sense in the future. This is 3.3. And then the last case, which is honestly the most annoying one in a certain aspect, but it's also the easiest one computationally, it's just the most annoying to understand, is when it's repeated roots. So that's when it's equal to zero. So what we get is repeated roots. One repeated root. Now, if you're wondering, does this idea extend to any size of differential equations like fourth order or fifth order, second order, sorry, third order? Yes. But the equation isn't as nice. Like if you think about a third order differential equation like three derivatives, this whole idea still works. It's just there's no quadratic formula. It's a nastier formula. But everything we're talking about in terms of principle, using e to the rx, it works. So e to the rx works for any nth order differential equation. It's just finding the solution is way more algebraically intensive because there's not a nice quadratic formula for it. So that's kind of the idea. So 3.1, we are going to investigate the real distinct root case. Like that's what we're going to focus on. So real roots distinct. R1 does not equal R2. So if you think about this, this is what I am saying. Okay. So for a solution where you get two roots, R1 and R2, we are saying that y equal to e to the R1t and y equal to e to the R2t are solutions. That's what we're saying. So let's verify that that's true. Like, let's actually solve one and see if we get something that works out like that. So let's do an example. And then we're going to dive more deeply into like that solution and like what it actually means, the combinations of the solution, any multiple of the solution. But let's just start at the most fundamental level. Okay. Solve the differential equation. They're not really gonna tell you which one it is. You kind of have to know from just solving the quadratic formula, right? So like that's really where it's gonna come from. So solve the differential equation y double prime minus 5y equal to 0. Okay. Actually, you know what? Just to make our life easier so that we're not looking at the weird case yet, or it's not a weird case, it's just like I don't want it to be where it's in this one we're not doing the full process. Here we go. So y double prime minus y minus 12 equal to 0. So when you're solving a differential equation of this type, it's all going to be the same process. Step number one, write down a formula. So step one, formula. Now, what formula you write down is just whatever you need to help you remember. So, what I write down, okay, is this. I write down AR squared plus BR plus C equals 0. I remind myself this is the style of differential equation I'm working with. And then I write where y double prime equals r squared, y prime is equal to r, and then y is equal to 1. Now, if you're wondering, where did that come from? We'll go back to how we solved it originally. When I plugged in y double prime, look right here, we got r for y prime, r squared for y double prime, and then y doesn't have anything in front of it, so we use a 1. Okay, so that's really where it comes from, is the coefficient of e to the rx for each derivative. Okay, so that's where those come from. Step two, plug in differential equation. So y double prime becomes r squared minus r minus 12 equals 0. If you really want to, you could use x if you like working with x, as a quadratic. The only problem is x is an independent variable, so do make sure that you change it eventually, but you could use it if you wanted to. All right, step three, solve quadratic. So, a word of advice, and I tell this to every single math class I ever teach. If you cannot factor something in 15 seconds, don't waste your time trying to factor. I tell you this because number one, not everything is factorable. Like you're never guaranteed something is factorable to begin with. Number two, if you spend 2 minutes trying to factor something, you would have done the quadratic formula faster, just going straight into it. So if you look at a quadratic equation and you can't factor it quickly, just do the quadratic formula. You'll get the same answer. I'm going to use the quadratic formula just to show you that this is factorable. So r is equal to negative b plus or minus the square root of b squared minus 4ac. Notice that 2a divides everything. I have noticed sometimes that people don't divide everything by 2a, they only divide the radical. Do you know that it's dividing everything? So this is a, b, and c. So r is equal to negative 1. So a lot of times people do mess up the negative negative scenario. Just be careful. Square root of negative 1 squared. If you do not put parentheses around that negative sign, your calculator will not read it correctly and you'll get the answer wrong. So please, 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 if you're plugging in negative numbers into a formula, especially when they're being squared, you got to put parentheses around them. It's a very common mistake, and I get the emails about that one a lot. So just make sure that you're paying attention to that. And then we plug in everything else. A would be 1, C would be negative 12, and then divided by 2 times 1. And if we just simplify a little bit, 4 times 12, I believe, would be 40, nope, 56. No, that doesn't sound right either. 48, it was 48. I was right in my head. 48. And here we get square root of 49, which I hope we all know, but if we don't, calculators exist. It's 7. And then we get 1 plus 7 over 2, or 1 minus 7 over 2. And then the result is that we get 4 or negative 3. So that is our roots. If you notice, right, whichever you call R1 and R2, it's irrelevant. It doesn't matter. They're not going to care on the homework. Um, but if you think about this, where is the differential equations? Like, where is it? It's step one. The formula is the differential equations. The differential equations was everything we did before we started the problem. It was that derivation we did earlier. We did the differential equations there. This isn't differential equation. This is algebra, right? Like this is really an algebra problem, which is what makes calculus and differential equations so difficult. Every step of diffie-q and calculus is very tiny relative to the algebra you put into getting that answer, right? So the quadratic formula is probably the most difficult step of this entire thing. So I have my roots R1 and R2. Well, now I just write my solutions down. Okay, so step 4 is solution. Y is equal to e to the 4x. I apologize if I swap between x and t. Sometimes they don't tell you which one it is, and I usually default to t. In the homework, it looks like they use x a lot, so I'll try to stick to x. And we get negative 3x, right? Those are solutions. If I plug these in to the differential equation, they will both be equal to 0, right? So I have answers right there. I'm done. That's the answer. But we think about this very deeply and we think to ourselves, okay, if this works, what if I put a number in front of like e to the 4x? Like, what if it's 2e to the 4x? I mean, it's just twice as big, right? So you start to think to yourself, okay, suppose y is equal to 4e. No, I guess it's a different number, so they're not the same. 3e to the 4x. And we check if it is a solution. So y double prime minus y prime minus 12y is equal to 0. If you take your derivatives, right, y double prime, oh, sorry, let's do it this way. Y is equal to 3e to the 4x. Y prime is equal to 4 times 3 is 12e to the 4x. And then y double prime is equal to 48e to the 4x, right? Chain rule. That's what's going on. I'm just doing the chain rule. And you think to yourself, okay, actually, let me just do it here. I get 48 e to the 4x minus 12 e to the 4x minus 12 times 3 e to the 4x equal to 0. And you get 48 e to the 4x minus 12 e to the 4x minus 36 e to the 4x equals 0. Well, these just all cancel each other out. You get 0 equals 0. So, what do I accomplish in this idea? Well, if e to the 4x works and 3e to the 4x works, then that means any multiple of e to the 4x works. So that's what we're going to claim here is that for any solution to a second order linear homogeneous differential equation, any multiple of a solution is also a solution. So notice how I wrote y equals e to the 4x as an answer and y equals negative 3x is an answer. Now what I'm saying is that y equals c1 e to the 4x or y equals c2 e to the negative 3x are answers. I'm just building up the solution because usually I would just go straight into like what the final solution is, but I think this is a good scenario where I can kind of build how the solution works, and eventually we end up combining these into one solution. But that's where the nature of where does that C1 and C2 come from, right? Where does this constant come from? Well, it just turns out that any multiple of your solution is still a solution. We just showed that. Um, okay, this is not a true proof because I'd have to show it for every single number, right? But the idea is there. We have just showed that any multiple of a solution is still a solution. So then this begs the question. I don't want to have to keep writing like this one's a solution or this one's a solution, right? Well, in mathematics, the word or means one or the other or both. We use an inclusive or in mathematics. So then one might reason, wait, if one is a solution and the other one is a solution, what if I combine them together? Would that also be a solution? Does that work too? Well, let's investigate, right? So we would say, okay, now suppose we do C1 e to the negative, sorry, positive 4x plus C2 e to the negative 3x. Um, is our solution, right? Suppose y equals that. Didn't give myself enough room. So suppose that is our solution. Well, what do we do to prove something is a solution? We just take derivatives, right? So we do that. And I just want to make sure I write this. And we check if it is a solution to y double prime minus y prime minus 12y equals 0. Now, this is going to be time consuming to some degree, but I promise you, you'll never have to show this. We're just going to assume that this is fact. But I want you to understand where it comes from because sometimes when you do these, you're like, why are these two being combined? And this will help you understand linear combinations a little bit more because that's kind of like a difficult subject to understand the first time you hear it. So hopefully this kind of bridges that gap just a smidge. So when you take derivatives and they're being added together, you can take them individually. There's no interactions here. So 4c1 e to the 4x plus negative 3. So we'll do a minus 3. C2 e to the negative 3x. And then if I take a second derivative, then we're going to get 16 c1 e to the 4x, and then plus 9c2 e to the negative 3x, right? Like that's our solution. And then we're just going to plug it into the differential equation. And if everything goes the way that we expect it, we should just have everything cancel each other out. So that's y double prime plus, and then we get 4c1 e to the 4x minus Sorry, that's not a plus sign. That should be a minus sign. I just saw it right there. And then this should be minus 3c2 e to the negative 3x. And then minus 12 times c1 e to the 4x plus c2 e to the negative 3x. And that's all equal to 0. And I'll give myself more space. So that's y prime, and that's y. Well, if we distribute everything, right? 16c1, and then minus 4c1 e to the 4x plus 3c2 e to the negative 3x minus 12c1 e to the 4x minus c2 e to the negative 3x equals 0. 16 minus 4 is 12, minus 12 is 0. 9 plus 3 is 12. Oops, I forgot to distribute the 12 there. Minus 12 is 0. There we go. So we get 0 equals 0. So what does this prove to us? That when you combine the two solutions together, they also form a solution, right? So that is our final claim. For any second order, linear, homogeneous, differential equation, the sum of any solution is also a solution. Thus, y is equal to c1e to the 4x minus, sorry, plus c2e to the negative 3x. That is the true solution to this differential equation. Now, you'll never have to prove that or show that. You'll just go straight into the final answer. So let us bring that all back to a new example where we don't talk about that at all and we just go straight into solving a differential equation. To be clear, and I didn't say this explicitly, we call this section the constant coefficients. So notice that in slide 2, I said that P of x, Q of x, and R of x, they're constants. We are only looking at this from the perspective of constant solutions, sorry, constant coefficients. So do be aware that this does change slightly when you get into the realm of non-constant coefficients, but we're not going to investigate that in this class. So let's solve a differential equation. Okay. And let's do this one right here. 2y double prime minus 5y prime minus 3y equals 0, right? So we're not going to think about theory anymore. We're just going to practice mechanics, right? Like that's what we want to learn in this example. So we're going to say, okay, step 1, what is my formula? AR squared plus BR plus C equals 0. And then Y double prime equals R squared. Y prime is equal to R. Y is equal to 1, right? That is the main formula that will carry you through this entire chapter if you just memorize that. I promise you. All right, step 2. We're going to plug into formula. So 2R squared minus 5R minus 3. A common mistake I see with people is they think y with no derivative is r. It's 1. So just be careful with that one, especially when you don't have all three of them. Sometimes they only give you two of them, like y double prime and y, or y double prime and just y prime. Please don't accidentally add one that's not supposed to be there. Put one in the wrong spot. All right. Step 3, solve quadratic. Again, I personally cannot factor this because it has a 2 in front of r squared. It would take me too long. So I just go into quadratic formula. I'm not even going to try. I have no shame in using the quadratic formula. It is very powerful. We thank the mathematicians that have created it in the past, right? So then I plug everything in. That's A, that's B, and that's C. So we get -5 plus or minus the square root of -5 squared minus 4 times A, which is 2, and then C is -3, all over 2 times 2. And then through some simplification, we get 5 plus or minus the square root of, again, 49. That's what you end up getting inside the radical over 4. And so then R is equal to 5 plus 7 over 4, or R2 is equal to 5 minus 7 over 4. And then R1 is going to be equal to 3, or R2 is equal to -1/2. I will tell you right now, okay, this is for those who decide to watch the video and actually partake in this. On the exam, you will rarely, if never, if ever, have a radical as your answer, okay? Fractions, probably. Whole numbers, almost always. I rarely ever see them use radicals. The only problem is with radicals, it just becomes a pain to do the algebra. Okay. Now, with at least with real roots, when it comes to complex roots, radicals aren't that bad, but even then, they typically avoid them. So if you're taking the exam and your roots are really bad, like they're like the square root of 14, I would just double check before you commit to that answer, just because usually they like to prefer fractions or whole numbers, or sorry, integers. It just on an exam it makes more sense. On the homework they can throw whatever they want because it's homework. I'm just giving you a little tip for the exam is you should double check if you get a nasty number. Chances are you may have done it incorrectly. So those are the roots, right? Now step 4. Uh, classify roots and plug into answer. Now, this is going to make more sense in the future when I have more than one case, but every single second order differential equation that has real distinct roots always has this solution. Y equals C1, it's not a 1, e to the R1t plus C2 e to the R2t. So y is equal to C1 e, what we get, 3, plus C2 e to the 1/2 negative t. Now, if you're wondering, where did t come from? Why isn't it x? That's just because I used the letter t instead of x for this problem. There's no reason why. I never told you whether it was x or t, but on the homework, they're way more specific for you. And they tell you in the directions which one to use, okay? Using t. So that's the answer. That's literally it. That's the whole process. So we're going to build up this decision tree eventually of doing differential equations, but let's start that tree right now. So, decision tree. Could never spell that word correctly, so that's probably wrong. So the first thing you ask yourself is it first order? Okay, sorry. Differential equation. All right, is it first order? Is it second order? Right? Now, right now, we don't care about first order because we're not doing that. Okay, when you get to second order, you have two questions. Is it linear or is it nonlinear? Okay. If it's nonlinear, we don't care because we're not doing nonlinear, right? But if it was nonlinear, you would just use Runge-Kutta. There you go. You're done. It's Runge-Kutta. We don't really cover it in this class anyways, but that's what you would do. Okay. If it's linear, well, you have two options. Is it homogeneous or non-homogeneous? Because that makes a difference. Okay. If it's homogeneous, well, it's easier. If it's non-homogeneous, you got to do extra stuff, right? And then you're going to have three cases. You're going to have R1 does not equal R2. R1 is equal to I, and then R1 is equal to R2, right? And right now, we're doing this one. Okay? So that means the solution to this one is y equals c1 e to the r1t plus c2 e to the r2t. I'm going to fill this out and make it look nicer in the future, but that's the tree, right? There's your answer. Complex has its own solution with sine and cosine, and then imaginary has their own solution, which is very annoying to deal with because it's not an exact solution. It's kind of like you kind of work with what you have and you modify it as you need it. But that's distinct real roots in a nutshell. So let's do an example where maybe they try to mess with you. So the easiest way they can mess with you in these types of problem is they just make the equation shorter. They give you less information. So solve 64y double prime minus 9y equals 0. This isn't any different. It's the same process. It's just if you're not paying attention, you might plug in the wrong thing, right? Step one, formula. That's why this formula step is so important because it tells you what exactly everything is, right? So y double prime is r squared, y prime is r, and then y is 1, right? So step two, sub in. 64 y double prime becomes 64 r squared minus 9. Now here is where people would put r on accident, but it's not r because it's not y prime, so it's not r, it's y, which means it's 1. So 1. Now, could you do the quadratic formula for this? Absolutely, but you don't have to. This is one of our favorite quadratics because if you're missing the r component, you can just solve for the variable using the square root. So what I mean by that is you can move the 9 over like that. You can divide both sides by 64, and that would be 3, no, 9, no, that would look like that. Probably is divisible, but I'm just not seeing it in my head. So I'm going to take the square root of both sides, like that. And then r is equal to plus or minus 3 over 8. There you go. That's the answer. And then step 4 is plug into solution. So r1 does not equal r2, so y is equal to c1 e to the r1t plus c2 e to the r2t. And then now I just plug in R1 and R2. Now, does it matter which one I call R1 and R2? Absolutely not. Does not matter. But sometimes in the directions, they might say like C1, sorry, R1 is the smaller of the two or bigger of the two. So as always, read the directions to make sure that you plug it into the correct spot if necessary. But it doesn't really matter. And there you go. You're done. That's the process. Again, they're going to try to trick you by getting rid of one of them, and you just have to be aware of that. And just for completion, let's just do the other one, right? What if they say solve the differential equation y double prime minus 8y prime equals 0, right? What if they do that instead? Well, as long as you're doing the formula, you should not be tricked because you know exactly what everything is. And so y double prime is r squared, y prime is r, y is 1. Step 2 is we're going to plug in. So we get r squared minus 8r equals 0. So whenever you get a quadratic of this form, this is the best one of all of them. This is your favorite one because you just got to factor out an r and you're done. So step 3 is solve for r. Sorry, quadratic. So r squared minus 8r equals 0. They both share an r. Now it's in factored form. You always get 0 as one of the solutions. Um, and then you get 8 as the other one. And then step 4 is plug into solution. Y equal to C1 e to the R1t plus C2 e to the R2t. And so y is equal to C1. Now, this is kind of an interesting one. So pay attention to this. I plug in 0. Remember, e to the 0 is not 0, it's 1. E to the 0 is 1, which means you're not going to have two exponentials, but rather you're going to have C1 plus C2 e to the 8t, like that. That means any constant is a solution, which is nice because if you think about it, if y equals 5, what's the derivative of 5? 0. What's the second derivative of 0? Well, if we plug in 0 and 0, you get 0 equals 0, right? So that makes sense. The derivative of a constant 0, so any constant works for this one. So we've done every variation of how they could mess with you. If you're wondering, what if they don't give us a second derivative? Well, then it's not a second derivative problem anymore. It's a first order, and you got to do integrating factor or separation of variables. So they can never do that because that would be tricky, right? I mean, it wouldn't even be a second order. Back to chapter 2. So what if they give us boundary conditions or initial conditions? How does that change the process? Not a lot. The only thing that happens is it just becomes more tedious because now you have to do an extra step, which is solve for C1 and C2. But it's not anything that you couldn't do or haven't been able to do. It's just you're going to have to do a little bit of algebra and potentially have to solve systems like, two by twos or, elimination method, if that sounds familiar, or maybe like a substitution method. That also can be a thing as well. So that's what we're going to do next. And so let's do an example. So solve the differential equation. So let's do this one right here. Okay, let's make it simple. So, if you're also wondering, what's the difference between initial and boundary? Initial is all of the numbers inside the parentheses have to be the same number, and they have multiple derivatives. So, like, notice y of 0, y prime of 0. Boundary just means that that limitation is not there. You can use whatever you want. So, they both can be at y, they can be at a derivative or not. It's just, it's not the same, following the same independent variable. An example people give often is if you're doing initial conditions, your goal on like a bullseye, like a dartboard, is just to hit the board, whereas a boundary value problem is you're trying to hit the board in a very specific spot. So when you're doing initial value problems, we're just hoping we hit the board. We want a solution. If you're doing a boundary value problem, you want a very specific solution and you can miss, right? So like even if you hit the board, you can miss the one that you want and it doesn't work either way, right? Kind of an analogy for that. Step one, formula. AR squared plus BR plus C equals 0. Y double prime equals R squared. Y prime is equal to R. Y is equal to 1. Right? Step 2, plug in. So the whole initial condition stuff, it doesn't come until the very end. So the first four steps, same thing as always. You're always going to do this. I'm telling you right now, the first four steps that I'm doing, you pretty much do in every single problem for this entire chapter. Like almost every single problem will require you to do it. I guess with the exception of 3.2 because it's slightly a different section. But other than that, you're pretty much doing this all the time. Okay. You know what? This is factorable. So let's just practice an example of factoring. Like I said earlier, if you're not good at factoring, use the quadratic formula. Don't waste time. But if you're wondering, how do I factor something like this? Well, I'll remind you a factoring technique that I learned, but everyone has their own factoring techniques. I've seen many different styles. This is just what works for me. So I asked myself, okay, what two numbers, right, it's called the AC method, right, multiply to the last number, 30, and then what two numbers add up to the middle number, negative 11? And then I just go through process of elimination. So 1 times 30, 2 times 15, 3 times 10. Uh, and then I do 4 doesn't work, 5 times 6. And then all I ask myself is this question. Can I add or subtract these numbers, negatives and positives, to get to 11? Well, 30 and 1, nowhere near. 2 and 15, best I can get is 13. Nope. 3 and 11, 13. 5 and 6, 5 plus 6 is 11, so that's a good candidate, right? So then I say 5 times 6, 5 plus 6. But I want a negative 11, so I make them both negative. And then a negative times a negative is positive, so it works, right? Like, there we go. And so what we end up getting is r minus 5 and r minus 6 equals 0. So then r equals 5 or r equals 6. Again, if that is too much work because you're not comfortable factoring, trust me, I was not comfortable factoring until I started teaching it, then just use the quadratic formula. There's no shame. Please don't think there's shame in using the quadratic formula. We love it. So we got our answers. Step 4 is to plug into solution. Doesn't matter which one you call R1 and R2, you get the same answer. So y, not y1, we're not there yet. Y is equal to C1 e to the R1t plus C2 e to the R2t. So then y is equal to C1 e to the 5t plus C2 e to the 6t. There you go. We have our, so we call this the general solution, and we'll talk more about that in 3.2, but this is the general solution. Now I want to find a particular solution, so we call it, where we have conditions, right? So that's going to be step 5. So step 5 is solve for C1 and C2 using y of 0 equals 0 and y prime of 0 equals 1. So because we have a derivative, that means you will have to take the derivative, right? So y is equal to c1e to the 5t plus c2e to the 6t. So if I take the derivative, chain rule says 5c1e to the 5t plus 6c2e to the 6t, right? You just do the chain rule. Let me write this off to the side. The derivative of e to the rt is r e to the rt. I should have written that down earlier. So y of 0 equals 0 means 0 equals c1 e to the 0t. Nope, that's correct. 5 times 0 plus c2 e to the 6 times 0. And again, remember e to the 0 is equal to 1. Please, it's not 0. I know you want it to be, but trust me, it's not. 0 equals c1 plus c2. There we go. And we now have y prime of 0 equals 1. So then 1 is equal to 5 c1 e to the 5 times 0 plus 6 c2, not c1, e to the 6 times 0. So then 1 equals 5c1 plus 6 c2. So those are the equations that I have to solve. Now, how you solve these will depend on your comfort in linear algebra. So if you have taken linear algebra and you want to use row reduction using matrices, please, please, please do that. You can do that on the exam. If you don't feel comfortable with linear algebra because you haven't taken it, then you're going to either use substitution method or elimination method. Substitution method is the one that I recommend for most people until you practice elimination enough. And all substitution does is just pick a variable in one of the equations, isolate it, and then plug it into the other one. So we're going to take this equation, we're going to isolate C1, okay? So C1 equals negative C2, and then we're going to sub in. So 1 equals 5 C2 negative plus 6 C2. And so 1 is equal to negative 5 C2 plus 6 C2. And then 1 is equal to C2. So C1 is equal to negative 1 because C1 is equal to negative C2. That actually worked out really nicely. Sometimes the constants could just be very ugly. Looking at the homework, you might get a nasty constant, sorry, a coefficient, which is unfortunate, but on the exam, they don't typically are that nasty. Um, Thus, our final solution is going to be, now, this is super important. Make sure you put the right C1 and C2 in this correct spot. I've seen people do all the work correctly and they mix them up. They just put them in the wrong spot because it does matter where you put them. E to the 5t plus e to the 6t, right? That's C1, that's C2. And that's the answer to a second order homogeneous linear differential equation with constant coefficients with repeated roots, sorry, with real distinct roots. Now, one last thing I want to talk about is long-term behavior. So this is going to be way more important in the section 3.7 and 3.8 using limits. So there might be a homework question where they ask you like, what is this function doing as t goes to infinity, right? So, example, how does y behave as t goes to infinity? Well, if you take the limit as y, no, wrong letter, as t goes to infinity for y, well, that's just going to be the limit as t goes to infinity of negative e to the 5t plus the limit as t goes to infinity of e to the 6t, right? If you just plug in infinity, you would get that. And it's just infinity, right? Well, technically, it's you wouldn't say it's infinity because negative and positive, but uh, we'll just say infinity-ish. So for us, we're just saying in the long run, it's just going to behave towards infinity, right? But if you get something like the limit as t approaches infinity of like e to the negative t, well, then you're going to get e to the negative infinity, which is equal to 1 over e to the infinity, which is 1 over infinity, and 1 divided by infinity is really just 0. So in the long run, we're going to say that that function kind of just zeroes out or decays to 0. And in the future sections, we might call this like damping or some kind of transient solution, actually. That's what we're going to call it, the transient solution. So that's going to be something that you're going to be looking at in the future. To be clear, this right here is actually indeterminate. And the reason is because it's negative infinity plus infinity. We can't really tell. So it's not actually infinity. But, we're not in that you know, not to worry about. You don't have to think too much about it. So, just an idea that's going to come up on the homework is this idea of how does my solution behave as I go to infinity? Very important, and it'll make much more sense in 3.7. One other thing, if you're wondering, like, and if you've gotten to 3.7 and 3.8, here's the beauty of it, right? You know what? You already know how to do 3.7, actually. Like, you do. Because all that changes, you know, for 3.7, instead of AR squared plus BR plus C equal to 0, you know what it is instead? It is MX double prime plus let me make sure this beta. I use beta, but some other things use other ones. X plus KX equals 0. Well, guess what? The solution is right here. Let's see. E to the divide everything by K. We're gonna use lambda, and lambda means something, but there you go. Lambda is equal to, I gotta remind myself, sorry. And then we use lambda for like eigenvalues later, which is kind of funny. So I am just pulling it up to remind myself. Again, you don't have to memorize this right now. We're going to talk about this later. I'm just telling you that, believe it or not, you already know how to do 3.7. It's just instead of A, B, C, we change it to mass, damping, and the spring constant, which is K. And so our solution ends up being uh, beta over 2m for mass. So something like that. It's a little more complicated, so I'm not going to dive too deep into it. Actually, I'm not even going to write that. I'm just going to say it's R1 and R2. That's even easier. R1 and R2. But you'll learn that eventually. And there's no R squared there, sorry. And there's no R there. Sorry. I'm just writing it out. There we go. It's the same thing. Just R's beta, M, and K.